Hello, Namaste. This is Rohini Mergu from Walchan Institute of Technology talking about divergence theorem solution part 2. In the part 1, I have explained the LHS part of divergence theorem. In this part 2, I will be explaining the RHS part of divergence theorem. Here I have taken the case of cylindrical coordinate system in order to explain the divergence theorem solution. Learning outcomes. At the end of this video, you will be able to apply divergence theorem for a given field. You will be able to verify divergence theorem in cylindrical coordinates. Before proceeding further, let us recall what is divergence theorem. Divergence theorem relates the surface integral with the volume integral. It states that the outward flux of a vector field through a closed surface is equal to the triple integral of divergence of a vector field from the volume element. So, closed surface integral of d bar dot ds bar is equal to volume integral of del dot d bar dv. So, I have taken a case here, this question, where I want to derive the both sides of the divergence theorem for a given question, like that is given d bar. This d bar is in cylindrical coordinate system and these are the ranges given, and for this we are going to verify the divergence theorem. So, we have already done the LHS part in the divergence theorem part 1. So, let us recall the answer or solution part of the LHS of the divergence theorem. So, when we have solved it, the LHS part, closed integral of d bar dot ds bar of LHS part we got as 225 coulomb for a given case. Why I am showing this, because when we solve the RHS part, we should be able to verify it with the LHS. So, we must know what is LHS. In the part 1, we have calculated LHS 225 coulomb. Now, the RHS is volume integral of del dot d bar dv or triple integral of del dot d bar dv. So, as this part, there are two things like volume integral as well as del dot d bar. So, before going to volume integral, let us first determine the del dot d bar in cylindrical coordinate system. Why cylindrical coordinate system? Because given d bar is in cylindrical coordinate system, so we are explaining it in the cylindrical coordinate system. So, del dot d bar can be given as 1 upon UVW dou by dou rho in cylindrical, so it's rho VW d rho, then dou by dou phi VW UW d phi plus dou by dou Z UV dz. So, this way I can write the equation of del dot d bar. This is one standard equation that I can follow. And what are this UVW? UVW are multipliers in cylindrical coordinate system. So, let us recall the multipliers in various coordinate systems. So, multipliers in various coordinate systems, like in Cartesian, UVW, the coordinates are xyz, but UVW are 1, 1, 1. In cylindrical, the coordinates are rho phi z and multipliers are 1, rho 1. In spherical coordinate system, the coordinates are r theta phi, multipliers are 1 r sine theta. Let us focus on the multipliers in cylindrical coordinate system because we are considering the case of cylindrical system. So, this is a cylindrical coordinate system having the coordinates as rho phi z, having the multipliers 1, rho 1. So, let us modify del dot d bar equation in the cylindrical coordinate system with the multipliers 1, rho 1. So, divergence in cylindrical coordinate system can be written or can be calculated from the standard equation. I can put UVW as 1, U as 1, V as rho, W as 1. Then by dou rho, VW. So, V is rho, W is 1. Likewise, I go on putting all these things, and when I simplify, I get del dot d bar as 1 upon rho into dou by dou rho, rho d rho, plus dou by dou phi, d phi, plus dou by dou z, rho dz. Beyond that also I can simplify, because this rho has nothing to do with the derivative with respect to z. So, this rho will be coming as a constant outside. So, let us multiply this 1 by rho inside the bracket and simplify further. So when I multiply this 1 by rho inside the bracket, this is 1 upon rho, dou by dou rho, rho d rho, again plus 1 upon rho, dou by dou phi d phi, plus 1 upon rho, dou by dou z dz. Now this rho and this rho cancels out, everything else remains as it is, so I get this equation. So this is nothing but the simplified equation of divergence in cylindrical coordinate system. See, this is just the equation of divergence, still I have not substituted my case here. So this is divergence in cylindrical coordinate system. Now let us take the case which we are solving, that is d bar, this d bar. So for this d bar, here the part along with a rho bar is d rho, so this is d rho. The part along with a phi bar is d phi, so this is d phi. There is no term of az bar, so dz is 0 here. So I can put these values in my equation of divergence, that is del dot d bar. So in this del dot d bar, I can put this d rho, I can put d phi, I can put dz. So when I substitute the values, I get the equation like this. So this red one is the values have been substituted at the respective places. Now simply solving it further, so you can see here 6 is and sine 0.5 phi is constant, can be taken outside the derivative. So inside the derivative, that is dou by dou rho, rho square. Again here the blue one is shown as a constant, which is 1.5 rho, can be taken outside here, and dou by dou rho is with respect to cos 0.5 phi. Again when I simplify it further, I can get dou by dou rho, rho square as 2 rho, whereas the derivative of cos 0.5 phi is minus 0.5 sine 0.5 phi. Then you can see here this comes to be 12 sine 0.5 phi, because the 6 into 2 is 12. This row cancels out with this row, so it comes to be 12 and sine 0.5 phi as it is. Here 1.5 into 0.5 will give me minus 0.75, minus sign because there is minus with 0.5, and sine 0.5 phi as it is. This is only del dot d bar, still we have not calculated RHS. So let us go to find out RHS of the divergence theorem. RHS is del dot d bar dv. So I have calculated del dot d bar from this del dot d bar, and this I need to put here. So I have put that value here with respect to dv. But what is dv? dv is the volume, differential volume, which should be written in cylindrical coordinate system, because given d bar, given field is in cylindrical system. So dv, to find dv, let us recall the differential volume in cylindrical coordinate system. Volume is nothing but the multiplication of three lengths, that is d rho, dz and rho d phi. And volume is of course a scalar quantity. So dv is nothing but multiplication of d rho, rho d phi dz. So this is dv. This dv I can put in my equation. So dv is rho d phi dz, that can be put here. Del dot d bar, which I have already calculated. Now let us take separate out these integrals. So integration of rho d rho. This is the phi part, so it's taken with respect to d phi. This is integration of dz. Now rho d rho will give me rho square by 2, limits as given in the question 0 to 2. This is 12 as it is. Sine 0.5 phi, when I integrate it gives me cos 0.5 phi upon 0.5. Then minus 0.75 as it is. Again sine 0.5 phi has taken the integration, and the limits are 0 to pi as per the question. The integration of dz is z, limits are 0 to 5. And if I simplify further, I can put the values here, like you can see here. Rho is 2 square by 2 minus 0. Phi, once it is pi and once it is 0. So this is substitution of upper limit, this is substitution of lower limit, and z 0 to 5 will give me phi minus 0. So the values here is 4 upon 2 is 2. Then you can see this part here is 24 minus 15. Then integration of this 0 to 5 is 5 minus 0. So I'll get here 2 into 22.5 into 5 minus 0, which finally gives me the answer as 225 coulomb. as we have seen at the starting that LHS which I have calculated in the part 1 is also giving the answer as 225 coulomb, and RHS also giving the answer as 225 coulomb. This part is calculated in the part 1 divergence theorem solution part 1. This we have calculated in this video, divergence theorem solution part 2, and both the cases you can see the answer is 225 coulomb. So I can say that divergence theorem is verified. And it is not only true for only D bar, but for any vector field, this divergence theorem, that is this equation, is going to be true. These are the references used for preparing this video. Thank you.